In this lecture, I would like to discuss ergodicity. Ergodicity is a fundamental property of measure-theoretic dynamical systems, and it essentially says that the system cannot be decomposed into two simpler systems that then can be studied. We already came across a notion of indecomposability when we looked at topological Markov shifts. There we called it irreducibility, and it was defined as the ability to reach any state from any other. So in particular, the system could not be broken up into smaller systems that kind of are connected within themselves, but not to the other parts, because in irreducible Markov shifts, everything is connected. So every state, every part of the system is connected to any other part of the system. So ergodicity now is just a measure-theoretic version of this. So assume you have a measure-theoretic dynamical system. So we have a space X, and we have a transformation acting on that space, call it T, and we have a measure on this space. Then T is measure preserving with respect to this measure mu, which just meant that mu of A is the same as mu of T minus 1 of A for all measurable sets A. Suppose now we could do the following in the space X. We could find complementary set, or we could partition X into two sets A and B that are invariant set theoretically with respect to the transformation T, in the sense that A maps into itself with respect to T and B maps into itself with respect to T. So TA is subset A and TB is subset B. And we would have that the measure of A is strictly contained between 0 and 1. And since B is the complement of A, this would also hold true for B, right, this condition. If we had that, then we could actually decompose X into two simpler systems, namely the system consisting of A and the system consisting of B, right, and study these two systems now separately because of these conditions here. They don't interfere with each other as T runs on them, operates on them. And measure theoretically, they're a little bit simpler in the sense that they have smaller measure than the full space X. So we could just split it up and study these two systems now individually. Ergodicity now says that precisely this decomposition here is impossible. So you cannot find such a decomposition. So let's just look at this as a formal definition again. So let X be mu and T be a measure-theoretic dynamical system. That just means that X and B is a sigma algebra on X, mu is a measure on this measure space, and T is a measure-preserving transformation of this space here. So now we call a subset of X T invariant if it is mapped into itself by T. The space X itself is called T decomposable if there exist disjoint T invariant subsets B1 and B2 that are measurable. So they are from the sigma algebra and they are of positive measure, so that they together give the space X. So they partition the space X. Right, and it's not hard to see that in this case we actually must have that the pre-image of each BI is BI itself. So this was precisely the picture we had on the previous slide. And a transformation T is called ergodic if the space is T indecomposable. So if we cannot find such sets B1, B2, measurable sets, then the transformation T, it's a property of the transformation, is called ergodic. There is a number of equivalent formulations of ergodicity, and I would like to point out just a few of them. So here are the equivalent statements. T is ergodic if and only if for all measurable B with a property that the preimage of B under T is equal to B, the measure of B is either 0 or 1. This is essentially just a reformulation of the original definition. The next one is a little bit more interesting. So this says if the measure, so if B is such that the measure of the symmetric difference, so this triangle here is the symmetric difference between the preimage of B under T and B itself is 0, then this implies that, again, the measure of B is either 0 or 1. This seems to be a stronger condition than the previous one. So here we have actual equality. So if we have in our space a set B, right here, in the second one we would have a set B that is identical to its preimage under T, right? Then this, whenever such a set exists, it must have measure 0 or 1. Now in this characterization, we only assume that the preimage of B under T is measure theoretically the same as B. So think of it this way. Whenever we have a set B, right, and now we look at the preimage of B under T, then it may not be totally completely identical with B, but the measure of the difference, so this thin sliver here, is 0. So here this measure would be 0. That would be the symmetric difference of this sliver, right? Whenever this is true, then the measure of B must be 0 or 1. So this condition here is weaker than this condition. So overall, this would be a stronger statement than this one. But nevertheless, these two statements are equivalent because one can show that if we had such a set B here that satisfies this, so the measure of this different sliver here is 0, but B had intermediate measures, so strictly between 0 and 1, then we could use the existence of that B by iterating the transformation T to build another set B prime that satisfies this. So that would then contradict this conclusion here. So the construction of this other set B prime is not completely obvious, but essentially it uses that an iteration of T and based on the existence of this original set B here. The fourth characterization is the following. If we have a set of positive measure, and now we look at the preimages of B under T, right? So the iterated preimages, and take the union of those, then we must eventually measure theoretically fill the whole space. And here again we can kind of intuitively see why this is true. Well, if we had such a set B that had positive measure, so assume here we had B, and now we look at the preimages, since t is measure preserving, we know that the pre-images all have the same measure as the original b, right? But they would all together eventually not fill out the whole space, so they would leave out some measure. So let's say it leaves out this part here, so they would only fill out this part measure-wise, right? Then again, we could throw all these pre-images together, right, and get an invariant subset of intermediate measure that would then violate the definition of ergodicity. There's an important alternative perspective on measure-preserving transformation, and it is from the operator theoretic point of view. Namely, any measure-preserving transformation T induces an isometry that means it's a distance-preserving mapping of an LP space, so LP space over X. Recall that an LP space for given real number P is just a set of all measurable functions that are integrable in this sense here, namely that the absolute value of f to the p is integral over mu is finite. And usually L0 just denotes the measurable function, so that you don't have any condition on integrability and so on. So these LP spaces are very important spaces in many branches of mathematics, specifically functional analysis and Hilbert spaces and so on. And there's a very powerful theory about these spaces that via this operator theoretic view or approach to measure preserving transformations can then be used in the study of ergodic or just measure preserving transformations. Now, if we have a measure preserving transformation T, we can define an operator on an LP space, right, for any P that sends LP to LP by letting ut of f just be f composed with T. Right. So now, since T is measure preserving, right, this implies that ut is an isometry with respect to the usual p norm. Right? So if you write everything out, so the p norm is just given by this integral here, and then take it the pth root of it, right? And then every norm induces a distance function, a metric, right? And then so the fact that T is measure preserving just means that this corresponding operator here preserves the norm that is given by this. And now we can formulate ergodicity as a condition on functions, measurable functions. Namely, if ut of f, so the image of f under the operator ut is equal to f mu almost everywhere, so that the set of points on which they agree has mu measure 1, then f is actually constant mu almost everywhere. That is, it assumes the same value on a set of mu measure 1. To familiarize ourselves a little bit with this alternative view, let's see how we can recover the original definition in this framework. So assume we have our space X here, and now we have a set A that is invariant in the sense that t minus 1a is equal to a. Now let's consider as our function f the characteristic function of A. So that means the function is 1 if the point is in A, and it's 0 if the point is not in A. Right? So what we have now is, suppose we have our condition now, ut of f is f mu almost everywhere, where UTF was defined just to be f composition with t. So this function f here is the characteristic function of A. So it just measures membership in A, right? Whereas this function first well, looks at transforms and then measures membership in A, right? So if those are the same, that means that the preimage of A, right, must be the same as A, and up to a negligible set from the point of view of the measure mu. Right? So the preimage now is more or less the same as the original set, so t minus 1a. And remember, this was one of the original conditions or previous conditions we had on one of the previous slides for when describing or characterizing ergodicity. Now the conclusion in the operator theoretic characterization says that then, if this is the case, then f is constant, mu almost everywhere. So in our case, that would mean that this function, the characteristic function of A, is constant mu almost everywhere. But that can only be the case if either mu of A is 0 or mu of A is 1, which is precisely the original conclusion with respect to the set theoretic definition. In the rest of this lecture, I would like to go over 2 examples of ergodic transformations. One comes from independent identically distributed processes, IID processes. So we call a stationary process ergodic if the shift map is ergodic with respect to the Kolmogorov representation. So we take the Kolmogorov representation of the process. We know, since the process is stationary, it will be invariant under the shift map. And then we say the process is ergodic if the shift map is ergodic for this Kolmogorov representation. So if the process is IID, then the corresponding dynamical system, right, based on the Kolmogorov representation, is not only ergodic, but something stronger, namely what is usually called mixing, or often strongly mixing. And this is this condition here. For any measurable sets A, B, the limit of mu of t minus 1 of A, so that you only take the pre-images with respect to t of A, and then intersect them with B, that this limit not only exists, which in itself is already a kind of a strong condition, but also is just the product of mu of A with mu of B. Let's try to illustrate the motivation behind this definition a bit, why it's called mixing. Well, let's look literally at a mixing process. So suppose you want to mix a martini and you add 1/4 vermouth to 3/4 of gin, and now you stir the whole thing, or you can, as James Bond once you can shake it. But let's assume we stir it, and now you would expect that if you stir it right and enough, then eventually the amount of, or the relative amount of vermouth should be the same in every region of the glass. So if I take a region here and call that B, then after stirring enough, right, then the relative amount of vermouth in this region should also be 1/4. Right? So formally, we would write this as, well, if T represents the mixing process, right, then this would be T minus N of A, where A is now the vermouth, intersect B, right, divided by mu of B, right? So the part of B that is after N stirrings is vermouth divided, right, relative to the whole measure of B, right? That should somehow become mu of A. And that's precisely what this formula here says. So mixing indeed is a mathematical way of capturing the idea that everything in the space is kind of well stirred and well mixed with each other. You can also think of it the following here. If you look at these as kind of events, A and B, then the stirring is so well that eventually the events become independent. So the A is stirred so well that any dependence that may have existed between A and B, right, is eliminated over time, and it just becomes they become independent events. Hence, their measures just multiply. And it's not hard to see that mixing actually implies ergodicity, namely, assume that we have T minus 1 of B is equal to B. So the assumption in the definition of ergodicity, right? And now we consider this mixing condition with A equal to B. So this means we just have the lim n of T minus n of A intersect, or rather B intersect B, right, is equal to mu of B squared, right? But this here, right, this is just B because we have T minus 1 of B is equal to B. So this here would just be mu of B. So that would be that mu of B is equal to mu of B squared, right? But this means that then that mu of B is either 0 or equal to 1. So mixing is stronger than ergodicity, and one can indeed show that it's strictly stronger. Now, how do we show that IID processes are indeed mixing? Well, the first one observes that, and that's not too hard to see, that it suffices to show the mixing condition for cylinder sets, so sets that then generate the algebra that generates the sigma algebra and so on. And for cylinder sets, we actually have an easy observation with respect to the pre-images. So the pre-images of a cylinder set under iterated pre-images are just the cylinder set that starts at n, right? If you recall, this cylinder set sigma n was just a set of all x such that xn is sigma 0, xn plus 1 is sigma 1, and so on, right? Assume now we have two cylinder sets, sigma and one given by tau. If n is greater than the length of tau, then sigma sub n fixes positions that are completely independent of the positions that are fixed by tau, right? So sigma, so tau would fix the first positions up to length tau, right? And then there's some freedom, and then there would be positions fixed by sigma, right? So this would be tau, this would be sigma, and then we would be free again to fill in the positions. But now, what is the measure of such a set here, right? We know that mu is a product measure since our original process is IID, right? Then it follows that the measure of the intersection, right, of sigma and tau, right, is precisely these kind of sets or of sequences I indicated here, right, is just the product of the measure of sigma up to n with the product of the measure of tau, right? But this measure here of the measure of sigma starting at n, since it's invariant, is just the measure of sigma itself. So it's the product of measure of sigma with the product of the measure of tau. So in the case of ID processes, it's really not that hard to establish this mixing condition. Finally, let's look at Markov chains. When is a Markov chain ergodic? Well, there we go back to our original correspondence. For Markov chains, we can really think of ergodicity as a measure-theoretic version of irreducibility. And now irreducibility, in the sense as we introduced it for Markov shifts, right? And we just look at now as at irreducibility for the underlying matrix, which in case of Markov chains was given by a stochastic matrix. And we call a stochastic matrix M irreducible if for any pair ij there exists an n such that m to the n, so the nth power of the matrix, the entry ij is greater than 0. So recall, this was just a probability that we can go from entry I, or from state I to state j in n steps. So there is some positive probability that we can go from I to j at all. So let's illustrate it with an example that is not irreducible. So assume we have a system or a Markov chain like this. So we have 4 states, 1 and 2, 3 and 4, and we go from 1 to 2 and 2 to 1 and stay in 1, all with probability 1/2. So in fact all the probabilities are 1/2 here, just as between 3 and 4, so 1/2, 1/2, and here we stay with 1/2, and we stay here with 1/2. Only here, these transitions between the two parts, right here, those are 0, and as are between these two parts. So there's 0 probability that we can go from one part, from the upper part to the lower part, and vice versa. And we start also with probability 1/2 in either part of the system. So this would be clearly a system which we would expect not to be ergodic, right? Because we could decompose it in the upper part and the lower part, and there's no interference between the two parts, right? So let's look at the corresponding stochastic matrix. So M would have the form 1/2, 1/2, 0, 0, 1/2, 1/2, 0, 0, right? That's the 1, 2 part. And then we would have a 0, 0, 0, 0 block here, and the 1/2 transitions between 3 and 4. And if you compute the power of this, you can actually see that this is actually the same as m squared, and hence the same as m to the third, and so on. So there you get the algebraic verification that there is no positive probability to go from this part into this part, right, which is represented by these blocks here. So this matrix M here would clearly be not irreducible. And as we will see on the next slide, this is actually the only obstacle for a Markov chain to be ergodic, namely it has to be irreducible. Here's the full characterization. So suppose we have a stationary Markov chain, and remember that meant not only that we had a stochastic matrix, but also an initial distribution which was invariant under the matrix, in the sense that P times M was P. And we also assume that there's no kind of superfluous state, in the sense that every state can be reached from the initial distribution. And so if we have that, then the following are equivalent, namely that the Markov chain PM is ergodic, is equivalent to the stochastic matrix M being irreducible, as we kind of intuitively saw on the previous slide. And here's yet another characterization of ergodicity for Markov chain, which is quite interesting and also very helpful, because it's often the easiest way to test whether a matrix is satisfies this, or the corresponding matrix Markov chain is ergodic. Namely, the Markov chain is ergodic if and only if 1 is a simple eigenvalue of the underlying stochastic matrix.